There's a new computer on the block, and it's not exactly your average Mac or desktop or the one in your smartphone. In fact, the chance of you owning a computer like this in the near future is basically zero. It's a computer so powerful that it's supposed to be able to solve problems in minutes that could take other computers 1,000,000,000,000 years. A technological revolution so profound it could alter the worlds of finance, data encryption, and pharmaceuticals, all in unprecedented ways. I'm talking about the quantum computer. Tech companies including Google, Microsoft, and IBM invest significantly in the development of quantum computing. We're talking hundreds of millions of dollars in just the past few years. But building a quantum computer isn't easy. It involves physics that stumped Einstein, and scientists have been running at this problem for decades without knowing precisely how to get there. These days, there are many kinds of quantum architectures. Several of them have seen big breakthroughs recently, bringing us ever closer to Q-Day, or the day when quantum computing gains the ability to do things like shatter the encryption that keeps most internet communications safe. I'm Jennifer Strong. As a longtime tech journalist, I've been covering quantum and its applications for almost a decade. In this episode, we ask what our future with quantum computers could look like. Is that future near, and what might it actually mean when companies start building them at scale? To understand quantum computers and their inherent mechanics is to understand the deep underlying nature of the universe. It's an attempt at figuring out both the randomness and the allure of the natural world, which is what makes quantum so fascinating and so complex. Welcome to The Next Innovation.
So I guess the way I would explain quantum computing is it's the next thing after AI. So it's a much more powerful way of doing computing, a very different way of doing computing as compared to how we do it today.
Jason Lynch is the CEO of Equal One, a quantum technology company. We spoke with him recently about what's shaping the quantum industry.
I mean, the way I kind of think about it is, with AI, we've abstracted the complexity, right? So typically, I think what a technology evolution story reflects is our engineers abstracting the complexity and moving it to a different level. And I think that's what we've done in AI, and that's what we're doing in quantum. So I think in the next 10 years, we will abstract the challenges of the, needing a PhD in quantum physics to understand the qubits and bring that up to, the application level so that people don't need to have that, and that it's not, it's not complex at that stage. You can understand what you're doing from an application.
Anything quantum is notoriously difficult to study. There's actually a running joke among scientists that if you claim to understand quantum physics, you clearly don't. It took decades for AI developers to translate neural cognition into computer systems, and even though most of us use some form of AI on a daily basis now, many of us don't know how it actually works. And with quantum, it's a lot harder.
The way to think about quantum, I think, would be we're sort of building a skyscraper on a different foundation. So the classical compute and AI is all built on digital. Quantum computing is built on something different, which is a quantum bit, or a qubit, it's called. And so what the industry is doing today is scaling up the number of qubits. We ultimately need to get to millions of qubits. We're at something like hundreds today as an industry. But, we're building that skyscraper, and when we have it built, we will have a much more powerful computer as compared to what you can do with even the most powerful computers today.
Isabella Ward is a physicist and staff writer at Wired. She previously covered quantum at Bloomberg. We asked her why quantum can be such a tricky science to understand.
So what scientists building quantum computers do is they use an atom or a particle of light or a tiny semiconductor to encode information, and then they exploit these quantum effects to compute a problem faster or more effectively than before. This was theorized 45 years ago by very prominent physicist Richard Feynman.
It takes a great deal of imagination to appreciate, because we're going to describe something which is different than anything you know about. This, in that respect at least, makes this perhaps the most difficult lecture of the series in the sense that it's abstract, in the sense that it is not close to experience.
And it's something that physicists have been working on ever since.
That little things behaved very differently than anything that was big. Anything that you're familiar with. Because you see, as the animal evolves and so on, and his brain evolves, it gets used to handling, and the brain is designed for ordinary circumstances. But if the gut particles and the deep inner workings were by some other rules and some other character, they behaved differently, they were very different than anything on a large scale, then there would be some kind of difficulty in understanding and imagining reality. And that difficulty we are in.
Feynman had a vision in the 1980s. He wanted computers to be able to operate like the natural world. Just how AI innovators wanted technology to speak the brain's language, Feynman figured computers should speak nature's quantum language. Except it's tricky. The subatomic particles that govern much of the universe, the electrons, protons, and tiny light particles, are unpredictable and unreliable. They have weird characteristics, like the ability to exist in two states at the same time, and they're extremely sensitive to external factors like temperature.
So the easiest way to think about it is normally when you have a bit, which all information is coded as a sequence of bits, the bit can be 0 or 1. And in quantum computing, you can store information that's both 0 and 1 at the same time.
John Martinis is a quantum scientist and executive who won last year's Nobel Prize in Physics. Computers encode information through bits, a series of zeros and ones. When grouped together, they form a binary code that tells the computer what to do, like exhibit a photo, make a sound, play a video game, and so much more. The quantum version of this is called a qubit. And qubits are unique. Often made up of subatomic particles like electrons, they don't have either value, and they can have both 0, 1, and every value between those numbers at the same time. One way to think of a qubit is like a coin. If you spin it on a table, it's both heads and tails at the same time. Qubits give quantum computers vastly greater processing potential than traditional computers.
So every time you add a qubit, you double the compute power. So quantum is an exponential technology, and that's used sort of a lot these days, not really meaning what it truly means, which is doubling every time you add a qubit. So one way to look at it is when we get to 100 perfect qubits, we'll have more compute than all of the compute that's on in the world today. So it's doubling every time you add a qubit. So and as I mentioned, the challenge is that they're very fragile. So you need to cool them down, typically, depending on what type of qubit you use, to keep them basically remove all the thermal noise. So you need to put them into in a special environment to keep them in the quantum state for as long as possible. And that's a lot of what the challenge is. We're sort of at hundreds of qubits, and the industry is trying to figure out architectures and ways of doing error correction, which is another big deal in the industry right now, where you're essentially using redundant qubits to make sure that you don't have errors and then correct them. So the industry today is scaling from hundreds to thousands and ultimately to millions of qubits.
There's a lot of discussion about quantum computing. It's very exciting. People have all these ideas. But one has to be a little bit careful that building a quantum computer is a little bit difficult. All the qubits have similar kind of problems. Each one's a little bit different. And if you want to really understand what's going on in the field, you have to understand, what are the problems and how you're going to fix it.
Building a quantum computer isn't just putting a bunch of qubits together. Because of their sensitive nature, most qubits need to be extremely cold, like outer space cold, to help them work properly. And because of their delicate quantum state, they need to be sheltered from physical vibrations or magnetic fields.
So what you need to do is make the quantum bits so that they have lower and lower errors, over time. And that way, if you want to do error correction and make a general purpose quantum computer, for example, it's easier if you just start with them lower. The other thing you have to work on is scaling them up and making thousands to millions of qubits, and figuring out how to do that, and figuring out how to do that in an inexpensive way. Most of these are pretty complicated physics experiments, needs complicated instrumentation, and you want to learn how to do that. And then you want to make your qubits fast, so just like your regular computers, you want them fast. So there's a bunch of, very simple metrics that you have to do. And then, of course, you have to get everything to work all at the same time, which is hard.
And yet, when all of these conditions have been met, the promise of quantum can be eye-watering. The basic nature of a qubit is that it can provide a multitude of probabilities at the same time, which is what makes them such an attractive asset for industries like logistics and pharma.
What's really interesting is you can map the quantum physics of a molecule into qubits, into this quantum computer, and then solve that problem much more efficiently. So for me, that's one of the big applications of a quantum computer, because there's this natural mapping and there's a need to solve these kind of problems, quantum chemistry and quantum materials problems. And the simple example I like to give is we all want to electrify transportation for various ecological reasons. You need to have these rare earth materials to make the rare earth magnets. But because they're rare earths, they're kind of expensive. There's a supply chain issue and the like. Whereas if we had a quantum computer, we can think about maybe designing these materials in a better way to use not so rare earths, or to make it more ecological process or better process. You can make also an argument in terms of drug discovery and other chemistry problems where one could enhance our abilities to design molecules. Because, as we all see, we use computers all the day to design electronics, and simulation modeling is really important on a classical computer. And if we can extend that to quantum mechanics, I think that could have a very big effect.
Today's quantum applications are good at optimization problems, like helping logistics companies find more efficient routes, or pharmaceutical companies to discover new drugs, by providing a multitude of possibilities based on different variables, all at the same time.
There's a number of applications that quantum, people are excited about quantum on. One major one is optimization. So today, optimization, it cuts across every business in the world. If you look at logistics, optimizing how you do logistics, the challenge, I suppose, with our current compute is once you get to, a number of variables, it becomes very difficult to simulate that or to get the optimum answer. Quantum computers will do that extremely well. So, companies like logistics companies, airlines, banks, specifically for the European Space Agency, they're looking at optimization of space infrastructure and space payloads, and how they can, optimize that with quantum computers. And we've gone through a journey with them. I suppose what we're trying to do is work closely with our customers like the European Space Agency to understand their problem, to translate that into a quantum algorithm, and then to help them build the capability internally on how to use these quantum computers and how to scale with us as we go through the generations. Optimization is one big application. Another big one is simulation of chemistry. So, and here the pharma companies, anybody doing material science like batteries, and here the potential is that quantum can simulate the molecules much better than we can today. So, for example, with a pharma company, it takes something like 15 years and about 1.3 billion to bring a drug to market. And much of that is because we have to use human trials to test out how safe and how effective the drugs are. The hope would be that we can do some of that with a quantum computer, so we can simulate how these drugs interact with the human body and take out some of that cost and that time. So, accelerating drug discovery, accelerating new materials for batteries, for, much more sustainable materials.
Last year, Equal One announced a partnership with the European Space Agency. lending one of its quantum computers for satellite data processing. Quantum represents a huge step for the space agency as they explore the advantages and nuances for things like mapping the Earth. Gabriele Meoni is an innovation officer at ESA, the European Space Agency. He primarily focuses on exploring new technologies for Earth observation, and we asked him what it means to use quantum computing for things like Earth mapping.
You have these climate maps that are deployed at large scale, but they typically don't they have a very coarse resolution. But fusing these maps with local scale information, you could potentially improve the resolution. And we wanted to see if quantum computing can be used to generate maps by fusing data and have a better resolution. Today's technologies, when we talk about quantum computing, we always mention this keyword that is NISQ, that we mean we are in the near intermediate scale quantum era. So we have quantum computers with a more or less limited amount of quantum bits that can be implemented, but those bits are noisy. So that means they cannot store information or process information for an indefinite time because the noise destroys the coherence, but in general destroy the information that is that is held by the quantum bits. So because of that, you cannot implement too complex circuits there because the noise will destroy the information. And that's, of course, one of the challenges because that means that the scalability, so the complexity, of the algorithms that you can implement nowadays is quite limited. To also assess the usability or the potential advantages of the algorithms, of quantum algorithms, you will need, if you need more qubits on the one that you can actually use, you will need to simulate them. But simulate quantum algorithm is a challenge. And simply because if it was simple to simulate quantum algorithms, all the quantum algorithms, then probably quantum computing would be not needed. So it's a bit of a chicken and egg problems in the sense that to assess the benefits, you will need better machine.
ESA satellites generate large amounts of complex data that support Earth science like climate modeling and disaster response. In a broader context, quantum can also help with materials development and fluid dynamics. As the data continues to grow, so does the need for stronger, smarter, and more efficient processing capabilities, making quantum computers a promising alternative for better decision-making.
We have a project with them that aims to assess the benefits, let's say, of quantum computing in general for 3 use cases, regardless at the beginning from the hardware, and then to assess the implementation of some of these algorithms that they plan to have some advantages on their hardware. Of course, it will be given their hardware is a NISQ hardware, would be a simplified version of the algorithms. Some of the algorithms nowadays, talking about challenges, is that the ones that promise to be advantageous will require the so-called fault-tolerant quantum computing, so with much higher number of qubits and no noise in general.
Equal One's computer, the Bell 1, operates on spin qubit technology, a version of qubits built on semiconductor chips like silicon. Spin qubits allow for millions of regular-sized qubits to fit on a standard semiconductor chip, making the computer easier to scale. In some cases, spin qubits can operate at warmer temperatures than the expected colder-than-space cryogenic environment, making costs and maintenance a bit easier.
There's lots of different types of quantum computers. There are quantum computers that are based on atoms. There's the quantum computers that are based on electrical circuits, which are superconducting and also spin qubits. There are quantum computers based on computing with light. So those are called photonic quantum computers, where light is going down fiber optics. But basically, you find some quantum phenomenon, and then you have to choose a quantum phenomenon where you can put the parts together and control it really well. For the case of superconducting quantum computing, which is what I'm interested in, we build integrated circuits made out of metal, aluminum, niobium, tantalum, fairly reasonable metals. And you have to lay that down very carefully, and you pattern that just like a regular integrated circuit into your quantum chip. And then that has to be cooled to very low temperatures, very close to absolute zero, where the thermal noise can be very small. And then you put control signals in that do all the quantum bit calculations for you to do that. And then at the end, you put in some microwave pulse, and then you can read out the qubit states and get the result of your algorithms. But it's really based on an integrated circuit. And the fact that, the currents and voltages in a proper integrated circuit can, obey quantum mechanics.
Equal One's vision as a quantum tech company is to build qubits on a standard semiconductor fab, essentially democratizing the way one installs and accesses a quantum computer. Their vision for the Bell 1 is to use it to operate as a standard rack, making installation easier.
Typically, they're massive infrastructure. You need very specialized cooling to get these qubits down to almost absolute zero. You need specialized vibration for the lasers that some companies use. Our belief and our thesis from the beginning was that if we can build this on a standard semiconductor fab, that we can make these much smaller in a form factor that goes into data centers today without needing any special infrastructure, without needing any extra cost to install the quantum computer. And that's what we've done with this first machine that we brought out, Bell 1 it's called. Basically a quantum computer in a standard rack. It just plugs into a standard outlet. It's a standard sort of, about 1.2 meters and, half a meter wide. So it's a standard rack that any other GPU or CPU would go into in data centers. So this is, a standard component that goes into data centers. You need no specialized infrastructure, and that's quite disruptive in quantum.
The way that Equal One and others are working with space agencies is an example of how quantum is starting to become useful. New York City saw its first quantum computer installed last year. It's made by the British startup Oxford Quantum Circuits, and it's mostly being used by prominent Wall Street banks and financial institutions that are exploring how quantum can help with risk mitigation, fraud prevention, data analytics, and more. What makes this quantum computer different is that it operates on both AI and quantum capabilities, something that many investors and scientists are eyeing.
I tend to think of it as just an alternative computer technology that can be more powerful. There are ideas, going back to the quantum chemistry problem, where you can use quantum AI to learn the chemistry of these molecules, and then you combine quantum AI with classical AI to solve the chemistry problems better. So there are some relationships. People have looked at that. They're a little bit different, but we think there should be some applications to it.
It's easy to frame quantum as the next big thing after AI, but the truth is much more nuanced. It took AI decades for its development to reach a commercial, consumer-facing market, and because of the nature of quantum physics, it's hard to picture a scenario in which quantum computers are mainstream tech devices. Here's Isabella Ward again.
I think the way we experience quantum computing is going to be fundamentally different to the way that we've experienced generative AI. There won't be a ChatGPT moment for quantum computing because it's just not a consumer-facing technology. These are highly specialized machines. They cost millions to build in many cases. There's not going to be very many of them in the world. Even companies using them, like pharmaceutical companies, some of them might have some in-house, but a lot of them, especially smaller businesses, will just pay for runtime on a cloud. So I would say that the average consumer who's, not totally plugged in with the tech world, I don't think they're going to see a revolution in the same way that we saw with when ChatGPT 3.5 was released.
And the precise timeline for when these massive computers will become commercially accessible is still being debated, which makes sense given this is ongoing research into some very different approaches to building these machines.
There's two things happening in quantum. One is, companies like ourselves are pushing the technology forward. And then there's other companies who are basically pulling in the requirements that you need to hit certain applications. So there's a massive amount of progress, a massive amount of momentum. So our view is it'll be sooner than that. Our view is in 4 to 5 years, you'll have quantum computers in the market, in enterprises, with companies using them to work on their biggest challenges. even, we have the smallest quantum computer in the world. It's in a rack. So I think, maybe one day we could have, quantum computer in our watch or in our car or in our home or in the phone. But one of the big challenges is that cooling. And while there's, various work being done on trying to increase the temperature, I think that's probably going to be, 25, 30 years down the road.
What we can say with any certainty is that the promise is bright, the optimism high, and tech companies are continuing to pour hundreds of millions of dollars into development. And it's possible that quantum's biggest role could be in how it gets combined with other technologies, things like making AI much smarter, and those effects may be closer than we think.
So I think what's interesting is we just have to see what happens over time, see how it evolves. And, I think there'll be some winners and there'll be some systems that don't work so well. But it's really hard to know until people build the systems and we just test them.
Thanks for listening to The Next Innovation. This series was produced by Situation Room Studios and powered by Enterprise Ireland, investing in the next wave of innovation. Our executive producer is Christine Barada, and our senior producer is Sharon Barrero. Additional production assistance by Global Situation Room. I'm your host, Jennifer Strong. Until next time.